It's just after 1:30 in the morning over the Pacific Ocean. A Boeing 737 cargo jet has barely left Honolulu when something begins to go wrong. In the dark cockpit, the pilots watch their engine gauges. One engine isn't behaving, power is dropping, the climb rate is falling. The lights of Oahu are already behind them, and there is nothing but black water below. They declare an emergency and turn back. Air traffic control offers a closer airport. The pilots accept. But as they struggle to keep the aircraft in the air, it becomes clear they're not going to make it to a runway. This is the story of Transair Flight 810, a Boeing 737-200 freighter that ended its flight not on land, but in the water, in a rare ocean ditching of a large jet with both pilots somehow surviving. In this video, we'll break down what happened that night after takeoff from Honolulu, how a cargo 737-200 ended up losing useful thrust in both engines, what investigators discovered about maintenance, oversight, and cockpit decisions, and the safety lessons this accident teaches, especially for cargo operations. Let's start with the basics: the flight, the operator, and the aircraft. Transair Flight 810 took place on July 2, 2021 at Daniel K. Inouye International Airport in Honolulu, Hawaii. The operator was Rhodes Aviation, doing business as Transair. This was a cargo-only flight, no passengers, just freight, operating on a regular inter-island route. The plan was simple: depart Honolulu, fly roughly 100 miles to Kahului on the island of Maui, a short hop of about 20 to 25 minutes in the air. Flights like this happen every night, quietly keeping island supply chains moving: mail, parcels, food, and other essentials. The aircraft was a Boeing 737-200C, a classic 737 variant that entered service in the 1970s. By 2021, most passenger airlines had retired these early models, but in the cargo world, older jets often live a second life. This 737 had JT-8D low-bypass turbofan engines, analog instruments, no modern glass cockpit, a main deck outfitted for freight instead of seats, and a long service history with thousands of takeoffs and landings behind it. On Flight 810, the crew consisted of a captain, the pilot in command, and a first officer. No flight attendants, no passengers, just two pilots up front and a load of cargo in the back. The weather that night was generally good. Visibility was acceptable, some clouds in the area, but nothing especially hazardous. There were no major storms, no strong winds, no heavy rain. On paper, this was a routine, straightforward leg. But as we know, accidents rarely happen because of a single factor like weather. They tend to arise when multiple issues line up at the same time. Shortly after 1:30 in the morning local time, Transair Flight 810 lined up on the runway at Honolulu. The takeoff clearance came through, the throttles were advanced, and the JT-8D engines spooled up. The jet accelerated down the runway, reached takeoff speed, and rotated into the night sky over the Pacific. For the first minutes, everything appeared normal. The 737 climbed away from Honolulu, the landing gear retracted, and the crew began to settle into what should have been a very short cruise segment before descending toward Maui. But then, the first warning signs appeared. The pilots noticed abnormal indications on the number 1 engine, the left engine. Engine parameters were not matching expected values. The engine wasn't producing the power it should for that phase of flight. The performance of the aircraft began to suffer. At low altitude, immediately after takeoff, the time you have to diagnose and react to an engine problem is extremely limited. The workload in the cockpit went up instantly. The crew informed Honolulu Departure Control that they were experiencing an issue and might need to level off and return. Air traffic control acknowledged, and from that point, the flight was no longer a routine cargo hop, it was now an in-flight emergency in the making. As the abnormal engine indications continued, the pilots had to juggle several tasks at once. Fly the airplane, keep it under control, maintain airspeed and altitude, diagnose the problem, figure out what exactly was wrong with the engine, configure the aircraft for best performance with reduced power, and communicate with ATC about their intentions and needs. They soon declared an emergency, telling controllers they had engine trouble and needed to return to Honolulu. ATC, in turn, started working to get them back on the ground as quickly and safely as possible. But because of where the aircraft was in relation to the island, controllers suggested an alternative, Kalaloa Airport, a former military airfield also known as John Rogers Field. Kalaloa was closer than Honolulu. In an emergency, every mile counts, especially if you're struggling to maintain altitude. The pilots agreed to head for Kalaloa. On radar and on the radio, you have a jet that has just taken off, now turning back, descending slightly, declaring that it has engine trouble and needs to land as soon as possible. But there was another problem. It wasn't just the left engine. As the flight progressed, the right engine, the number 2 engine, also appeared to be underperforming. It didn't fail outright, but it wasn't producing the full thrust needed to keep the aircraft climbing or even holding altitude at its current weight and configuration. Instead of the familiar scenario of one engine at full power and one engine shut down, Flight 810 was now in a gray area. One engine significantly degraded, the other not delivering full thrust, the aircraft heavy with fuel, and very little altitude to trade for distance. This combination made the situation far more dangerous than a textbook single-engine failure. With both engines not producing adequate thrust, the crew of Flight 810 found themselves in a classic but terrifying situation. They were running out of altitude before reaching the airport. In a jet, especially an older one like the 737-200, performance after engine problems depends heavily on aircraft weight, configuration, flaps, gear, drag, airspeed, too slow and you risk a stall, too fast and you waste energy, and the amount of usable thrust from whatever engines remain. Ideally, with one engine out and the other at full power, a 737 at the right weight should be able to at least maintain altitude and often climb slowly. But Flight 810 wasn't in that ideal world. With reduced performance from both engines and the aircraft still relatively heavy, they could not maintain altitude. As they descended unintentionally, the crew kept ATC updated. They indicated they might not make it to Kalaloa. Controllers and nearby resources began preparing for the worst, including alerting the U.S. Coast Guard. Think about the environment. It's the middle of the night. There's limited visual reference over dark water. The horizon can be hard to see. The coastline is still some distance away. The pilots are trying to fly the airplane, troubleshoot, manage checklists, and talk to ATC all at the same time. In this environment, small deviations in speed, pitch, or configuration can have big consequences. As the descent continued and the airport remained out of reach, the pilots were forced to confront an increasingly stark reality. They were not going to reach land. At that point, their remaining option was to attempt a controlled ditching into the ocean. Ditching a large jet in the ocean is an absolute last resort. There is no guarantee of survival. The structure is not designed for repeated impacts with waves. Water can tear apart landing gear, wings, and the fuselage. But for Transair Flight 810, ditching was the only path that offered any chance of survival. As they descended toward the surface, the pilot's priorities shifted. Maintain a safe airspeed to avoid stalling, keep the wings level, control the pitch attitude for touchdown, and avoid slamming nose first into the water. A stall close to the surface would almost certainly be fatal. A steep nose-down impact would be catastrophic. The goal is to contact the water in a relatively flat attitude with as little vertical speed as possible. In the darkness over open water, judging height is difficult. There are no runway lights, no visual slope indicators, just a black surface. At approximately this point in the flight, with no runway in reach and both engines not delivering what was needed, Transair Flight 810 impacted the Pacific Ocean. The airplane hit the water hard. The forces involved were tremendous. The airplane broke apart in the sea, scattering wreckage across the surface and sinking into relatively shallow coastal waters not far from Oahu. Inside, the pilots were thrown around and injured, but both survived the initial impact. They now had a new fight to handle, surviving in the water until rescue could arrive. Because the crew had been in constant communication with air traffic control, their approximate position was well known. The U.S. Coast Guard and other local rescue services had already been alerted before the ditching occurred. Search and rescue teams responded quickly. A Coast Guard helicopter headed toward the last known position, rescue swimmers prepared to enter the water, and surface boats also moved into the area. The dark Pacific at night is a hostile environment. Aircraft wreckage, floating debris, fuel, and waves all add to the danger. One pilot was found clinging to floating wreckage. The other was located nearby in the water. Both were injured, one seriously, but alive. They were hoisted into a helicopter or brought aboard rescue boats and then transported to medical facilities in Honolulu. For a large jet that had ditched at night, within sight of land but over deep water, the survival of both crew members was an unusually positive outcome in an otherwise serious accident. The airplane itself, however, was destroyed, resting in pieces on the seabed. With the immediate emergency over, investigators now turn their attention to understanding how a cargo 737 had ended up in the ocean so soon after takeoff. In the United States, major aviation accidents fall under the jurisdiction of the National Transportation Safety Board, the NTSB. Within hours, an investigation was underway. The wreckage lay in roughly a few hundred feet of water, shallow enough for a detailed recovery operation, but deep enough to require specialized equipment and coordination. The goals were clear: locate and recover the flight data recorder, or FDR, locate and recover the cockpit voice recorder, or CVR, recover the engines and other critical components, document the debris field to understand how the airplane broke up. The FDR provides a detailed timeline of the aircraft's performance: altitude, airspeed, heading, engine performance parameters, control positions, and many other data points depending on the system. The CVR captures audio in the cockpit, pilot conversations, radio calls, alarm sounds, and any other audible cues in the flight deck. Together, these recorders allow investigators to reconstruct the flight from both a technical and human perspective. In parallel, investigators examined the aircraft's maintenance records, the operator's procedures and manuals, crew training history, weather data, and the history of any previous anomalies or write-ups on the same aircraft and engines. Over time, a detailed picture began to emerge. Analysis of the FDR and CVR confirmed the basic outline. The number one engine showed abnormal behavior early after takeoff. Both engines ultimately provided insufficient thrust for the aircraft to maintain altitude at its weight and configuration. The crew attempted to return to land, but ended up ditching when they could not reach an airport. But investigators wanted to know why the engines weren't performing as they should. Maintenance and performance data indicated that the engines, especially the one that first showed problems, had a history of issues. Over previous flights, there had been abnormal indications, including signs that the engines were not always delivering the power expected under certain conditions. These included irregular engine temperatures, performance shortfalls, and other data points that suggested the engines were aging and not operating at peak capability. The investigation raised serious concerns about how thoroughly those problems had been diagnosed, whether they had been fully corrected, and whether the operator's maintenance program provided enough margin of safety given the age and condition of the fleet. On the operational side, the CVR and FDR revealed how the crew diagnosed and responded to the problem, how quickly they recognized the severity of the engine issue, which checklists they used or did not use, how they applied single-engine or reduced thrust procedures, and how they managed airspeed, configuration, and flight path as performance deteriorated. The NTSB ultimately identified a combination of factors rather than a single root cause. Inadequate maintenance and oversight leading to engines that were not as reliable or capable as they should have been, crew decision-making and checklist execution that was not fully aligned with best practice under the circumstances, and systemic issues in how the operator and regulators monitored the condition of aging aircraft. One of the major themes in this accident is the challenge of operating older aircraft safely, especially in cargo roles. A 737-200 is perfectly capable of safe operation if it is maintained rigorously, monitored closely for performance trends, upgraded or repaired promptly when issues arise. But older jets require more attention, not less. Components wear out, engines accumulate thousands of hours. Small discrepancies, slightly high temperatures, slightly low thrust, can be early warning signs of more serious problems. In the case of Transair Flight 810, the NTSB found that the engines had repeated indications of abnormal behavior prior to the accident flight. Those signs were not fully resolved before the aircraft returned to service. The operator's overall maintenance and safety culture were not at the level needed for that type of operation. Regulators were also drawn into the picture. The investigation raised questions about whether FAA oversight of the operator was sufficiently robust, whether the systems in place to catch patterns of recurring issues were working as intended. When maintenance culture and regulatory oversight both have gaps, older aircraft can gradually drift into a state where they are still technically airworthy on paper, but their real-world performance margin has been quietly eroded. Flight 810 exposed that vulnerability. The investigation didn't only look at metal and machinery, it also looked at the human side, how the crew reacted in a rapidly developing emergency. In a simulator, engine failures are usually clean and obvious. One engine suddenly loses all thrust, you identify it, shut it down, and fly on the remaining one. Checklists are run in a controlled environment, often in daylight, with no surprises. Flight 810 was not like that. Here, the crew faced a partial loss of thrust, not a clean failure, confusing or ambiguous engine indications, a second engine that wasn't providing full performance but hadn't failed outright, nighttime conditions over water with few visual cues, a heavy aircraft at low altitude. Under intense time pressure and stress, the pilots had to interpret evolving engine data, decide which procedures applied, choose whether and when to reduce power, shut down an engine, or configure for single-engine flight, all while fighting to keep the airplane climbing or at least not descending. The NTSB identified areas where cockpit actions and decisions did not fully match best practice or company procedures. These included how the crew diagnosed the nature of the engine problem, how they managed speed and configuration with limited thrust, and how they applied checklists in the few minutes they had. The point wasn't to single out the pilots as the sole cause, but to show how real-world emergencies are often much messier than textbook scenarios. The report highlighted the need for more realistic simulator training that includes partial power situations and ambiguous failures, emphasis on energy management when performance is marginal, and strong reinforcement of standard procedures under high workload. If we step back and look at the broader picture, Transair Flight 810 is a classic example of an accident chain, multiple factors linking together. 1. Aging aircraft and engines. The 737-200 and its JT-8D engines had been in service for decades, requiring careful monitoring and maintenance. 2. Recurring engine issues. Prior abnormal performance and indications suggested that the engines, especially the one that first showed problems, were not in ideal condition. 3. Inadequate maintenance response. The operator's troubleshooting and corrective actions did not fully eliminate the underlying problems. 4. Oversight gaps. Regulatory systems did not intervene early enough to correct systemic issues at the operator. 5. Operational environment. Nighttime cargo flying, over water with limited diversion airports and low margins at heavy weights. 6. in-flight emergency in human factors, partial thrust failures, ambiguous data, high stress, and extremely limited time to act. 7. Outcome: insufficient thrust to reach land, leading to a ditching and the loss of the aircraft. Remove any one of those links, and the outcome might have been different, but on the night of July 2, 2021, they all lined up. Transair Flight 810 is especially important because it shines a light on cargo operations that the public doesn't see as often as passenger flights. There are several key lessons that emerge. First, aging fleets demand strong safety cultures. Older airplanes can be safe, but only if operators invest in high-quality maintenance, proactive replacement and overhaul of components, and detailed tracking of performance trends over time. Second, small discrepancies matter. Slight power shortfalls or recurring abnormal readings should be treated as early warning signs, not just minor nuisances. Normalizing problems can slowly reduce your safety margin. Third, pilot training has to reflect messy reality. Engine failures in the real world are not always clean. Training should include partial failures, gradual thrust loss, complex multiple failure scenarios, and decision-making under severe time pressure. Fourth, cargo safety must match passenger safety. Just because there are no passengers on board doesn't make a flight less important. The crew's lives, the aircraft, and people on the ground are all at stake. Safety systems, oversight, and culture should be equally robust. And finally, oversight has to be continuous and data-driven. Regulators and operators need to watch for patterns, repeated incidents, frequent write-ups on the same systems, signs that an operator's internal safety net isn't catching problems early. Transair Flight 810 was a warning sign that these patterns weren't being addressed aggressively enough.
Transair 810 stands out for several reasons. A large commercial jet ditched in the ocean at night, and both pilots survived, a rare outcome. It involved an older freighter, part of a segment of aviation that often operates away from public attention. And it exposed real weaknesses in maintenance practices and oversight that don't only apply to one company or one airplane. In modern aviation, serious accidents are rare. When they do happen, they are studied intensely so that the lessons learned can prevent the next one. From Flight 810, the message is clear. Pay attention to trends, not just individual events. Treat recurring technical issues as serious risks, not background noise. Train crews for realistic, messy emergencies, not just textbook failures. And ensure that cargo operations, no matter how small or out of sight, are held to the same safety standards as passenger airlines. You've been watching a detailed look at Transair 810, the cargo 737 that didn't make it back to land and ended up in the Pacific instead. If you'd like more deep-dive investigations into aviation incidents, especially lesser-known cargo and freight operations, consider subscribing to JetWhiz and turning on notifications so you don't miss future episodes. Let us know in the comments which other cargo accidents or near misses you'd like to see covered, and what you think are the biggest challenges facing older jets in today's skies. Thanks for watching. Stay curious, stay informed, and we'll see you in the next video.